All right, this video is going to cover work, the work energy theorem, and possibly some conservation of energy if we get that far. We'll see how it goes. So work is building off of the previous video on energy and the basics of energy with the types of energy. When we first defined what energy was, we said it is the ability to do work. So work is closely tied to energy. There's an importance there connecting the two, in that if an object has potential energy, or an object has kinetic energy, or even if there's some thermal energy present, these are all in some way defined under the ability to do work. So if energy is present, it means that work can be done. So we got to define what work is. We got to try and understand it in physics terms, and then we'll look at things like the equation to find the amount of work that is done. So work itself is defined not entirely differently than we understand it in a more regular sense of the everyday world, right? We say you go to work, right? You've got school work to do, you're working in the yard, whatever it is. So all these definitions imply, right? It's something that takes like some effort, and like whether you're thinking really hard for a test or homework, right? Homework for school is a form of work. Your job might be really thinking intensive. Maybe you end up working as an accountant or something like that. Or it could be physical labor, like maybe you're working in construction and there's some work you have to do. And that also, right, chores or work around the house, you might lift things, clean things, move things. So, work in physics does connect, and the definition for work does connect to all those things. And we'll explain what the definition is, and then we'll talk about how it connects to our understanding of work, even outside of physics. So, work in physics, well, work is when a force, and we'll pause here to say work is not the same thing as force. Work is what occurs when a force acts parallel to a displacement causing a change in energy. Now, before we dig into connecting this to some examples of working in the yard or schoolwork or your job, um, we can see there's sort of a cycle here of if there's energy present, if there's some form of energy, then there's an ability to do work. So there's this ability for, and that goes back to the definition of energy. We said energy is the ability for a force the ability to exert force and cause change. Those words are both showing up, right? Force is acting when work is done, change is happening, change in energy. So there's a cycle of energy exists, which allows for work to be done. So because of energy, there can be forces that are acting parallel to displacements, which we'll talk about in a bit, and causing a change in energy. And when that energy changes, we're going to get into more detail later about forms and types of energy and conservation of energy, but you might go from potential to kinetic energy. So a change in energy might mean that some of your energy that was potential energy is now kinetic or vice versa, but you still have some energy. So, and we'll get to conservation and all of that later on. But the fact that there's still energy means now more work can still be done. So there's this idea that energy allows for work to be done. Work changes energy from like one type into another, and then you still have energy, which means work can be done. So there's all the things that occur around us throughout the entire universe is just part of this cycle, right? It's in some ways you could talk about the types of energy that are available and whether the things that happen in the universe will go on forever, or eventually will all energy turn into a form that's not really usable, and then like the universe kind of dies. But that's a really, really, really long time in the future if something like that happens. Um, so not to be doom and gloom about that. But really the dynamic changing nature of energy and work is that energy is changing forms all around us. There's potential turning to kinetic. In class, we might have looked at or look at some of the examples of this or how energy changes from one type to another, and we'll continue to do that throughout this unit. And there's lots of really neat ways, like even if you look at photosynthesis, like the energy from the sun goes into the plants, and then the plants make their own energy and their food through photosynthesis, and they grow, and then an animal eats the plants and converts that into energy, and then maybe you eat the cow or whatever, and then the cow's energy becomes your energy, and it's a cycle of these changes in energy that happen all around us occurring because of work. So all the changes in energy happen because force acts parallel to displacement. Okay. So we're going to write an equation for this. We're going to write a variable for it. It's going to be a really important part of Unit 3. So the variable is W, which makes a lot of sense. It is not a vector. We'll look at, when we see the equation, there will be positive or negative work, which we'll talk about once we get to work energy theorem, but work by itself is not a vector. It doesn't have a direction that we assign to it. Okay, units. Now, work has the same exact units as energy, also joules, which is going to make a lot of sense once we look at work energy theorem, because we're going to set work and energy in some ways equal to each other. So they both would have units of joules. So same units as energy, work has units of joules. All right, the equation for work. So the two things that were mentioned, both of which we now have some context for. We understand forces from Unit 2. We understand displacement from Unit 1. The force acting parallel to displacement, those are the two main physics values that are mentioned in our definition of work. And they are the two values exactly that show up in the equation. Work is equal to absolute value of force. Now, I'll pause to mention here, this could be any type of force. Gravity could do work. Pretty much any of our forces can do work. Applied force could do work. Friction could do work. Normal force doesn't really do work hardly ever. That one's a bit of a weird one there, but friction can do work. Tension could do work. All the forces that we've encountered could do some work. Okay. Oh, and also I'll finish the equation, but I never connected it back to actually it'll be nice to have this equation. I never connected it back to like all the ways that we do work in our lives. There's displacement, so absolute value force times absolute value displacement times the cosine of the angle between them, theta. So this is the angle between the force and the displacement. So we'll come back to this. We'll draw some little images that hopefully help depict or show, like, here's work happening and here's a force and here's a displacement. How do we draw it out or visualize it or find what the angle is between force and displacement? So we'll be using a few different examples of that in a little bit. But let's connect it back to like doing work. So you go to your job. Let's say it's like a physical job, and today they have you lifting and moving some boxes, or maybe you're full on construction where you're like smoothing out the road that they're repaving, or digging along the side of the road with a shovel as they're working on the road. So all this work requires force, right? So if you're lifting something, moving something, shoveling, like smoothing a surface, whatever it is, operating machinery even, right? There's some force involved. You're going to push, you're going to pull, you're going to use applied force and all that. And you're going to move things, right? If you're shoveling, you're like moving dirt and the shovel. And even if you're just moving the machinery of something you're driving, a machine at work, that would also be force acting, causing displacement to occur. So all of those things, not only what you do, but even what the engine of, if you're driving a Bobcat or you're driving a cement truck as a construction worker, the engines of the vehicles themselves are also doing work. There's forces that are happening. There's forces acting from the engine and the wheels and the axles, and that force is causing displacement because you're driving or moving from one place to another. So all these examples of like more physical labor, raking leaves, right? You're putting the force into raking the leaves in your yard and you're moving them, you're causing displacement to happen. So that's work as well. One of the harder ones to think about is more like mental work, right? Like schoolwork, or if your job makes you just think really hard and use your brain a lot, even if you're sitting in a desk or in one place. So how does that play in? Well, that one's a little harder to visualize or see, but even in your brain, when you sit down and work really hard on a test, or you're puzzling over some physics problems on a problem set at home, you are using force to send signals through your brain because neurons firing and everything that's happening inside your brain to be like, all right, I got to remember how to solve this work problem, or what was the equation for kinetic energy again? How do I use it here? As you're thinking really hard about that, all of the signals and things that are happening in your brain that are being sent to recall information uh, and to solve a problem and to think about the situation that you're presented with and what are my known variables and how do I do the units again for this, right? Or even writing a paper or something like you're thinking of how should I phrase this sentence in my paper for English class. All of that requires energy because there's forces on a small scale in your brain. There are forces acting parallel to displacements. So um, there's forces causing the electrical signals and the neurons to fire, and these little small particles and things, right? The little signals that are being sent in your brain are moving through your brain and then through your body, and there's signals that are sent, and then your muscles contract to write. You're writing your paper, or your brain tells you to go into your backpack and pull out your calculator or your equation sheet to work on your physics problem. So there are less obvious forces. They're not as intense pushing, pulling, or lifting as like physical labor, but there's still forces happening. So all of these forces, both all of these work examples require energy. If you are really tired or you haven't eaten, right? The two biggest things are getting rest so we can have energy available in our bodies and food. So if you haven't done those things, you're going to find it a lot harder to rake the leaves in the lawn or to lift things at work or to think really hard about that physics test or that paper you're writing because the available energy in your body to do that work is less, and your body's like, hey, I don't have a lot of energy to put out force and cause displacement and cause changes in energy. I just There's not a lot of available energy. We might have mentioned a little bit in class sort of ATP, and if you've taken biology or even AP bio, the stored chemical energy in your body is we take food and break it down and then you get ATP. So anyway, I'm not going to talk for too long about that, but it's neat to connect the physics definition to um, to sort of everyday life. All right. That being said, let's get back to some equations and things here. So here's our basic definition of work. We are going to look at some examples in just a little bit of work causing changes in energy with force and displacement and how theta, the angle or cosine theta, works into all this. But before we do that, we're just going to briefly mention this change in energy that happens. It turns out we have a specific theorem or equation, I guess, that connects to this, and we're going to look at the work energy theorem. And the work energy theorem simply states that um, the amount of work done in any scenario, we could have been one of the things we mentioned while you're raking leaves or lifting something or driving a vehicle or thinking really hard about your homework. The amount of work done is equal to the change in kinetic energy. Okay, so there's an equation for this as well that we're going to write out. It's pretty short, and it just says, well, we'll put it here in purple. The equation says work, the amount of work done, is simply equal to the change in kinetic energy. So work, you could use the work equation to find work, or say, okay, in this problem, I know some things about the force that's acting. I know some things about the displacement or that cosine theta, and I can find with the work equation, I can find the amount of work. Okay, well, that's equal to, that's the same exact thing as the change in kinetic energy. So this could be like you push something or lift something, and it was sitting still before, but you used your applied force and you pushed it or lifted it, and now it's moving. So that object didn't have kinetic energy before. It was sitting still, but then you did some work and you put a force on it and you caused a displacement to occur. And there's now some kinetic energy for that object because you moved it. So that's the idea behind the work energy theorem is whatever amount of work you do, that's how much kinetic energy is changed either from like potential into kinetic, or we'll look at kinetic to potential. You could even look at kinetic into thermal energy. And we'll see some various examples of that, those changes in energy as we go along. Okay, cool. So let's now, well, I guess real quick, I'll mention that changing kinetic energy, you could find that with K final minus K initial. So if a problem ever comes up where, I guess I'll use the 0 subscript. If a problem ever comes up where you have some information about mass and velocity, because remember that kinetic energy equation, to find kinetic energy, we use 1/2 times mass times velocity squared. So 1/2 mv squared is kinetic energy. And what we could do is, if we could find, well, what is the mass and velocity of the object at the end of whatever work was being done, whatever happened, what was the mass and the velocity of the object at the beginning of whatever was happening, we always know that final minus initial gives us the change in anything. So we could do 1/2 mv squared for final minus 1/2 mv squared for initial, and that would give us the change in kinetic energy, which we could then say, oh, well, that's equal to work. So it works both ways, no pun intended. You could use the work equation to find work and say that is equal to the change in kinetic energy, or you could just find the change in kinetic energy with kinetic energy final minus initial, and that would be equal to your work that is done. Okay, let's actually look at some scenarios because they'll allow us to get a better sense of what's going on with the cosine theta and the force and displacement. They'll also show us some of these changes in energy we're talking about, and yeah, I think it'll be really helpful. We'll talk about positive and negative work as we go as well. Okay, so we're gonna do some examples or scenarios of work being done, energy being changed from one form into another. So first off, we'll start with just like a box on the ground with some mass m, and we'll just have an applied force. In fact, we'll go so far as to assume that there's no friction here. And when our applied force acts on this object, we're going to say that it slides through a displacement. We'll say it goes from here to like here. There's your displacement, delta x. So you push on a box, there's no friction at all to oppose your applied force, and it slides or moves some delta x to the right here. And we can even draw the direction to show the arrow. There's delta x going to the right. So if we were to do the work equation here, it's not so much that whether the force or displacement are positive or negative. That doesn't really matter because our work equation has absolute values on force and displacement. They could have also both been to the left or like negative direction. You could have applied force to the left, the displacement is to the left. It doesn't really matter for the work equation whether the force or displacement are positive or negative. You could have them both be negative and the absolute value would still give you a positive number. But what we can note here is that for this specific scenario where the force that is acting acts to the right, causing the object to move with a displacement to the right, or affecting it as it moves to the right, this force is acting. When the work is done from applied force, we'd note that the angle between force applied and delta x, well, they're in the exact same direction as each other. Applied force is directly to the right. Delta x is also directly to the right. So the angle between those two things, those two vectors specifically, is 0 degrees. They're in exactly the same direction. There is no difference in the direction of the applied force and the direction of the displacement. Well, what does that tell us? It tells us, so the cosine of 0 is 1. And what that means is our work is positive. Just to scroll back up and check in with our work equation, the absolute value of that force doesn't matter if it's positive or negative. It'll just get absolute valued times the absolute value of that displacement, whatever it happens to be, times the cosine of theta. This is what really affects, well, it affects a couple things. We'll see an angled force in our third example where we actually have to use the angle the force is acting at and look at what's happening there. But in a lot of ways, this cosine theta really determines whether the work done is positive or negative. Because even though it's a scalar and we don't assign a direction to work, what we'll find out about kinetic energy and the change in kinetic energy is you could get more kinetic energy, so the change in kinetic energy could be positive, or you could lose kinetic energy. Not that it goes away or is destroyed, but you could get kinetic energy turning into something else, some other type of energy, in which case the change in kinetic energy would be negative. So you can have both positive and negative work. And we're going to show that in our second example. We'll get to negative work. But to add on to this, so there's no angle between them. They're in exactly the same direction as each other. Cosine of theta is cosine of 0, which is 1. And we get positive work, which means, see if I can find my, there it is. Work is positive, meaning the change in kinetic energy is also positive. Okay. So we're going to point out real quick what that looks like. Well, what type of energy did we start with here? So you are applying a force. You, the person pushing the object, are going to use your energy to put some force on this. Well, that's actually a type of energy that we don't really deal with a lot. We may look at applied force doing work, but when we do, we're not really going to ask about the type of energy that we start with to do that work, which is actually chemical potential energy. So stored in your body, right, in your ATP is where you store all of your energy, right? You break down food, you digest, you get the energy from it, and your body turns that into, if I can pronounce it, I, ATP something triphosphate, adenosine triphosphate. Shows my biology knowledge here. But I think it's adenosine triphosphate. Maybe I'm entirely mispronouncing that. We'll call it ATP. So the ATP stored in your body then is the energy that you use, right, to apply a force. So what happens here is the energy change that occurs because every time work is done, a force acting parallel, now we can see that parallel nature, right? Here's our applied force acting parallel to that displacement. The energy change, because it will cause a change in energy, is we're going to put U chem, that's your chemical potential energy stored in your ATP in your body, turns into kinetic energy for the moving object. So what you've done is you've taken some of your energy He said, all right, I'm going to use up some of my chemical energy. I'm going to exert an applied force on this object, and I'll be a little more tired after that. I'll use up some of my energy. And where's that energy going to go? Well, that energy is going to turn into kinetic energy because the object moves. So this object that wasn't moving, you put applied force on it, you cause it to move, and you turn that chemical potential energy into kinetic. That's why we have a positive change in kinetic energy, because we start off with no kinetic energy for the object, and then we end up with some amount of kinetic energy. So that is a positive change, going from 0 joules to, I don't know, 7 joules of kinetic energy, or whatever we end up with, is a positive change in kinetic because of the positive work. And that goes back to work energy theorem, right? If the work is positive, then you have a positive change in kinetic energy, a gain in kinetic energy. There's more kinetic energy than there was before. Let's look at some negative work, though. So here's another scenario with an object. And in this one, let's say it's already moving. So maybe this is after you gave it a push or something, but we're going to take away, we're not going to have your applied force anymore. We're just going to have some velocity. And remember from Unit 2, an important thing here is just because an object is moving with some velocity does not mean there has to be a force acting in the direction that velocity is at this moment. At some point in time, something or someone did exert a force to give this object its velocity. Something had to do work to convert to like potential energy to kinetic to get this thing moving. But now that it's moving, it just has some velocity. We don't have to have a force still pushing on it to the right. It just is moving. And it has some kinetic energy because of that, right? It's got a mass and a velocity. So 1/2 mv squared would tell us there is some kinetic energy present for this object. So what's going to happen now is friction is going to come in. So we're going to introduce friction. Because it's moving to the right, here's our friction to the left. And friction's a good spot to bring up and remember normal force as well. I could also draw that on our other images, so I'll go ahead and do that. So there's normal force. And we might ask, like, why did we not bring up normal force here? Why did that not play a part in the work that was being done or what's happening? We could add gravity too. We got gravity going on. We'll get a whole little free body diagram of sorts going here. I should probably make this one a little bigger, but that's okay. My normal force is just about as big as friction, which is fairly rare, but if you got a lot of friction, a big coefficient of friction, that could be possible. All right, so we got gravity, normal force, and friction. So why haven't we mentioned normal force or gravity like in scenario 1 at all? Well, the reason is both normal force and gravity are acting perpendicular to the purple displacement. So we could add in another thing here real quick, which is that up here, normal force and gravity are at an angle of theta equals 90 degrees to the displacement, because the horizontal displacement, delta x, that's a 90-degree angle between the horizontal displacement and FG, also a 90-degree angle between the horizontal and normal force. And because they're at theta of 90, cosine of 90 equals 0. And these forces do no work. They do 0 work. So even though they're acting, gravity pulls down on our object, normal force acts up on our object. In this scenario, because they are 90 degrees, right angle or perpendicular to the displacement, and the cosine of 90 is 0, if we tried to plug into that work equation, we say, okay, here's the normal force, and here's how far the object moves, and then cosine of theta, cosine of 90 is 0. So you're going to get 0 times force times displacement, and there will be no work done whatsoever by the normal force. Same thing here for gravity. Gravity can do work, but that would be like a falling object or something thrown up in the air or something in some way moving vertically. If your displacement is vertical at all, then gravity can do work, because gravity acts parallel to a vertical displacement. But if your object's moving side to side, if the displacement is horizontal, both gravity and normal force here are perpendicular to the displacement. So that means that they don't do any work at all. They do not cause a change in energy. The only force here of these three that is causing potential chemical energy to turn into kinetic is the applied force from the person. Gravity and normal force aren't doing work. They're not causing a change in energy in this particular situation. And the same thing with number two. We could say the object is still going to have a displacement that we'd put to the right. So we'll just go ahead and draw that here. It goes some amount of displacement delta x. And normal force and gravity are both at right angles to that. So no work done whatsoever by normal force and gravity. The one we are going to look at that does work is friction. So let's hone in on that. The angle between the force of kinetic friction and the displacement delta x is, well, now delta x is to the right and friction is to the left. So what angle is there between them? They're not in the same direction anymore. If they were both exactly to the right, or even in scenario one, even if the applied force and displacement were both to the left, there'd still be a 0-degree angle between them because the applied force pushes or pulls in the same direction the object is moving. But friction is an example of if that force that's doing work pulls in the opposite direction to where the object is going, there is a 180-degree angle between that force and displacement. So what does that mean? Well, let's look at it. So the cosine of 180 degrees, put that in your calculator to find out that it is -1. So what happens here when we put it in the work equation, we'd say, all right, here's your force of friction. Doesn't matter that it's negative or to the left, it's absolute value of force of friction. We'd put in the displacement. Okay, how far does it go? How many meters? Doesn't matter if it's negative or positive. Just put in the absolute value. And then cosine of 180 would be -1. So we'd get a positive number times a positive number times -1, meaning the entire work value that we get here is negative. So that's -1, and the work is negative, meaning the change in kinetic energy is also negative. Okay. Very cool. So let's look at what's actually happening here. So this object, it's sliding, it's moving, it has some kinetic energy. So we start off with some kinetic energy. The change in kinetic being negative means we're about to lose some of that energy. We're going to have less kinetic energy at the end than we did at the beginning. So what happens to it? Well, the object is going to slow down, so it makes sense that we're losing kinetic energy because the velocity after friction has been acting on it while it slides, however far this is, as it slides through some displacement while friction acts on it, it's going to slow down. Its final velocity is going to be less than its starting velocity, and it's going to have less kinetic energy than it did before. So what's happening to that kinetic energy? Well, friction, when it comes to work, whenever friction acts as objects move, specifically kinetic friction, notably static friction cannot do work because there has to be a displacement for work to happen. And if your object isn't moving with static friction, there's no displacement. So for a different reason, static friction will never do any amount of work because displacement is 0 if you've got static friction acting. If your object isn't moving, there's no work being done because there's no displacement. But kinetic friction can absolutely do work. And when it does, that kinetic friction, if you think of like just rubbing your hands together with friction, right? There's work happening there because your hands themselves are moving in displacement back and forth across each other. And there's an applied force when you rub your hands together, and you get heat along with sound. So same thing for like something sliding along the floor. You're going to get some amount of sound, unless it's really padded or really quiet, but some amount of sound as well as some amount of heat, which isn't really noticeable. Like sliding something along the floor of your room doesn't really noticeably heat it up, but there is some amount of heat energy, thermal energy, as a result of this happening. So what does friction do when it does work? Well, the energy change that's happening here when the applied force did work in part one, we went chemical potential to kinetic. Now friction is doing work. The energy change that happens is kinetic energy goes into thermal energy. Okay. So this particular change in energy is a weird one because I guess I don't need. I was trying to think how many. Honestly, I just do ETH. I don't know why I wrote THERM. You can do that if you want, but it's probably easiest to do the shortest subscript possible. So ETH is good. All right, so energy change from kinetic going into thermal is a lot harder to sort of go back from. We'll talk about conservative and non-conservative forces. We'll talk about the ability for work to be done from like kinetic to potential or potential back to kinetic. So kinetic energy turning into thermal means we lose kinetic energy. The change in kinetic energy is negative. We have less at the end, less kinetic at the end than we did at the beginning. And that's because of negative work. And friction is a great example or a common example of negative work because friction always acts opposite to the direction the object moves. If your displacement is to the right, friction is acting to the left. So because of that, we always get that negative work from friction. So friction always does negative work because it's always opposite to the direction of the displacement. So that's an example of when your force and displacement are 180 degrees in exact opposite directions, you get negative work. Now, there's sort of a third option of, we noted that perpendicular forces, normal force and gravity here, don't do any work at all. Forces that are in the same direction as displacement do positive work. Forces opposite to the displacement do negative work. Well, what about a force that's at some angle in between? We've seen angled forces in Unit 2, so we'll do one more example here. And it's not too complicated of one. So let's say you've got an object and you want to move it. So you put an applied force on it. But this applied force, we're gonna do it at an angle. Do a little steeper angle here. There's your applied force. And we're going to go through a displacement once again. So we'll draw how far it goes. I'm not going to put the gravity and normal force on there. Actually, if I did, one reminder from Unit 2 would be our normal force would not be just equal to gravity here because we've got additional upwards force from the applied force. So remembering that normal force is only equal to gravity when they're the only forces acting in that vertical direction for an object on a surface like table or floor. If there's additional force like applied force that is upwards or downwards, that will affect the normal force. But that's not the main thing we're going to look at here. What we're going to look at instead is the angle theta. There's the horizontal. That horizontal line then would be parallel with the displacement delta x, which I should put a variable down there. And let's put the angle in as well. So we've got some angle theta. I don't know, maybe this is like 30 degrees or 35 degrees or whatever it is. There's your angle theta. So in this case, for this angled force, the angle between the force and displacement is just, well, theta here. So the angle between the force applied, and the displacement, delta x, is just theta. And again, it could be whatever. It could be 30 degrees or 25 degrees or 35 degrees or whatever amount it is. A problem would tell you if you need to work with the number, Sometimes they don't, right? Sometimes you just use sine theta. Well, we just use cosine theta here, but we've seen problems that just use sine or cosine theta without giving you the number because you're just working with the variables instead. But if you need a number, they would give you one, like tell you what the angle is. Anyways, when you do this, we'd get the work is equal to, well, absolute value of force applied times absolute value displacement times cosine of whatever your angle is. And in this particular case, it would still come out to be positive work because the cosine of 30 or the cosine of 35 or 25 is still a positive number. It's not 1, which is interesting here. Like it's not just 1 for the cosine or -1 like our friction was. It's something like, I don't know, the cosine of 30 is 0.866. So you might get a positive times positive 0.866 here. So when you're dealing with an actual angled force that isn't just directly to the right, like our first example, or directly to the left, like our second, and that force isn't perpendicular, like gravity normal force, where they don't do any work, if it's at some angle like this, you'll get some amount of work, and you just use the angle between the horizontal displacement and the applied force here is just theta, the angle it makes with the horizontal there. So you plug that into the work equation and you find your answer. Well, so what is this telling us about this force? What it actually tells us is that I'm going to do some components here. We've got 2 components to this. There's FAX. I really don't have too much room to write this, but I'm going to try to sneak it in here and do my best. FAX. And then up here, going up on this side, we've got FAY. Those are the 2 components. So to find those components, we would use sine and cosine. This is back when we did angled forces and how to work with any angled vector. We did this with initial velocity, launch velocity for projectiles. We did it again with angled forces. We'll do a little bit of it again with momentum, but not a whole lot. So whenever we have these vectors at an angle, we split them into their components and say, well, the FAX, we would use the cosine of theta to find it. So let's go ahead and write out what that is. So FAX is equal to the cosine of theta. And then cosine theta is FAX divided by FA, because you want to do adjacent here, adjacent side FAX over the hypotenuse, which is the total applied force, just FA. And then to solve for FAX, we would multiply both sides by FA, which should feel pretty familiar, right? This is something we have seen before in a few different spots. Okay, so, and likewise, you could use the sine, but what I want to point out here is you could use the sine for FAY. I want to look at the cosine because in our work equation, we've got FA times cosine theta. So what that tells us is, in this scenario, because FA times cosine theta is in our work equation, what this means is FAX does work. It does some amount of work here, causing energy to change from one type to another. But FAY does not. Because if we look at that other component, FAY, it is perpendicular. FAY is perpendicular to the displacement delta x, whereas FAX is parallel to it. So there's sort of 2 ways you could do this. You could do the work up front of saying, I'm going to do cosine theta times FA because that will give me the component of this force that's actually doing work that is parallel to the displacement. And you could plug in the force as FA cosine theta, you could plug the displacement as delta x, and in that case, you'd have FAX and delta x parallel to each other, same exact direction. So then it'd be a weird one because you'd do cosine theta FA for the force times the displacement times the cosine of 0. But you've already accounted for the cosine of 30 or 35 or whatever this angle is by finding FAX. So that's one way you could do it. I don't recommend it necessarily. What I recommend is if you have an angled force like this, just go ahead and put the entire force FA into your work equation, put the entire displacement of how far it goes in for delta x, and then use the cosine of whatever that angle is. Because that way, the equation will do the heavy lifting for you of you don't have to first find FAX and then use that in the work equation. You can just say, I'm going to use the entire angled applied force, but because only FAX does work, the work equation, what it's doing for you, what it's already doing for you with the cosine, is it is only using the part of FA that is horizontal, FAX, to get your answer. It's not accounting for FAY. The work equation is set up so that it will ignore and not make use of FAY and is just using FAX to find how much work is done. Because that FAX is the force that actually, or the component of force here, that actually does work. So it's a little weird with angled forces, because you could have part of that force doing work, the x component here, and part of that force not doing any work, FAY. Because the horizontal push or pull is causing a change in energy here, but the vertical push or pull is not. Okay. Well, let's summarize. Positive and negative work. I guess we could mention here the energy change would actually be just the same as the first one, to be honest, because it's still a person's chemical energy. So we'll just mention again the chemical potential energy turning into kinetic. All right, let's look at some summaries of positive and negative work. So here's our summary. Of positive and negative work and our work energy theorem. All right, so the first we'll focus on the positives. So if the force that is acting, whatever it is, could be applied force, friction, tension could do work, gravity could do work, whatever it is. If the force and the displacement, and we'll add in with the force, this also could be if the force or a component of force, in that third example we saw, the only thing doing work was FAX, that component of the force. So if the force or a component of the force and displacement delta x are in the same direction, theta equals 0, we get positive work and a positive change in kinetic energy. So that's where like potential energy turns to kinetic. That's like the first and third examples where the force or a component of the force is acting in that same exact direction as displacement. Well, yeah. I should amend this a little bit because I don't want you to think like, well, in the third example, theta wasn't 0. We could say theta equals 0 or something less than 90. Because it could be a 30, 35, 40 degree angle here. So as long as it's something less than 90, you could even have a 70 degree angle for example number 3, and you'd still get some positive work. It wouldn't be as much positive work as if you pulled directly to the right, because you're kind of wasting some of that force. If you're pulling more upwards, then the part of the force pulling upwards isn't doing any work, and only the force pulling horizontally or to the right would do work. But you would still get some positive work as long as it's something less than 90. Okay, just a couple examples of that would be well, one of them we already brought up. So we could get potential chemical energy turning into kinetic. You could get gravitational potential energy turning to kinetic. We haven't addressed that just yet, but that's a falling object. So when something falls, the force of gravity does work as it falls downwards, and potential gravitational turns into kinetic. A spring launching something, which also we haven't looked at in detail yet, but springs can exert a force. When a spring exerts a force that's in the same direction as displacement, spring potential turns into kinetic as you launch something off a spring. And same with gravity is the force of gravity acts downwards in the same direction as the displacement for a falling object. So all these examples of potential energy turning to kinetic are positive work. That's positive work. Negative work. So if the entire force, like friction in the second example, or some component, you could have like, if we did example 3, but the force was acting backwards, opposite to the direction the object moves, we could have some negative work there as well. Something like applied force is capable of negative work. People can do negative work if they just put a force opposite in direction to the displacement of the object. So if the force or like in example 3, if a component of force if the force and the displacement are opposite directions, meaning that theta, and we'll put in the actual range here, is anywhere from 90 to 180 degrees. Then we get negative work. And a negative change in kinetic energy. So this is anywhere, in this example, anywhere between like where our normal force is, and if we had any force going backwards to any amount, whether it's friction or you could have an angled applied force pulling back at some angle or pushing back on this object as it slides to the right, that would also give you negative work. So 0 to 90 gives you some amount of positive work. 90 to 180 gives you negative work. I guess it should probably be like a less than or equal or something, because if it's 90 degrees exactly, you get no work whatsoever. But yeah, if it's somewhere between 90 and 180, you get some amount of negative work. Or if it's 180 exactly, like friction acting opposite to the displacement, you'll still get negative work. Okay, let's talk about what this is. Well, there's a few examples we could do. We could say the one we identified already was kinetic energy turns into thermal energy. That's a change in energy we saw. You could have an object that's thrown upwards. So when you first throw it up and it leaves your hand, it's got a bunch of kinetic energy. As it goes up, and we'll try to look at, we don't have time right now, but we'll try to look at some of these examples either in class or in problems. We'll see, okay, what direction is the displacement? What direction is the force? How do I set up the work equation? Is this positive or negative work, etc.? But this is like as an object rises up in the air when you first throw it up, the displacement is upwards because it's moving up, but gravity is acting downwards. So the displacement is up, gravity is down. Those are in opposite directions to each other. You're going to get negative work as kinetic energy turns into gravitational potential, because the higher and higher it goes in the air, it's getting more and more gravitational potential energy, and that kinetic is going down, it's decreasing because your object slows down as it rises up, and your kinetic turns into potential. Same thing for a spring. If you have an object that like lands on a spring, so maybe it's sliding to the right and it hits a spring, or it's falling through the air and it lands on a spring, it's going to slow down because the spring like catches it, right? As the spring then compresses, or even if you drop an object that's attached to a spring, maybe the object falls and moves for a while, but then the spring stretches out. And as that spring compresses or stretches to slow down the object, the kinetic energy turns into spring potential. Because now, if the object lands on your spring or stretches out the spring, which slows down the object, the kinetic energy is turning into stored spring potential energy. And we'll get more into that, especially with Unit 4 when we do springs and pendulums for simple harmonic motion. So we'll see a lot of these changes in energy sort of going back and forth. And we're not going to address conservative, non-conservative forces just yet. We'll come back to this and we'll talk about work energy theorem and positive or negative work, and we'll mention some things with conservative forces or non-conservative forces. But that can wait for now. Okay, so summary of work, positive and negative work. The work equation is absolute value force times absolute value displacement times cosine theta, and what really matters for positive or negative work is the cosine theta. Because if your force and displacement are somewhere in the same direction between 0 and 90, you get positive work and a positive change in kinetic energy, like potential turning to kinetic. If force and displacement are opposite directions to each other, somewhere 90 to 180, you get negative work and negative change in kinetic energy. The kinetic energy is turning into either thermal energy through friction or drag, creating heat or sound. Kinetic to potential if something's moving up in the air and slowing down. Kinetic turning to spring as something is like landing on a spring or stopped by a spring as the spring stretches or compresses, slowing down the object and turning that kinetic into stored spring potential energy. Okay. And the work energy theorem is super handy because every single one of these, if you do your math and you find out, maybe it's a number problem or maybe it's just variables, but you set up the equation, you say, here's how much work was done. Either it's, 12 joules of work, or you say, well, the work in this problem is, where's my work equation? The work in this problem is the force of friction, mu times normal force, times the displacement, however far it goes, delta x, times the cosine of the angle theta, which would be 180 if it's friction, so -1 there. And once you find either, maybe it's an equation for work that says it's mu times normal force, like mg could be normal force equal to gravity. So you might have mu times mg times delta x, and it's negative, and that's the amount of work. Well, work energy theorem allows you to always say that that work is equal to the change in kinetic energy. So the amount of kinetic energy that either turns from potential to kinetic or turns from kinetic into something else is always equal to that amount of work that is done. All right, we're going to do one sort of last thing just as an introduction or basics of conservation of energy, because I want to introduce just the definition of it and the equation real quick. We'll expand on it. We'll do more of that in the next video. I hope I have enough ability to write these here before I run out of letters or whatnot. All right, so conservation of energy. At a basic level, conservation of energy says, in fact, we'll call it the law of conservation of energy. The short summary is energy cannot be created or destroyed. It can only change forms. I know I'm getting to the end whenever I get weird random scribbles on my... All right, I think we can sneak in just enough extra writing here to get us there. All right, so energy cannot be created or destroyed. It can only change forms or types, I guess. Forms of energy, types of energy would be potential, kinetic, thermal, gravitational potential, spring potential, etc. So this claims that all this stuff that's happening in the universe, so in the entire universe, all throughout it, right? There's work being done constantly. Every process, if we think about the back to the essential question, the ultimate source of all processes in the universe is energy, which means every single process that happens around us is work being done, energy changing from one type into another. You drink from your water bottle, you run outside, you watch an acorn fall from a tree, the sun burns its fuel and gives off heat and light. All these processes, every biological, natural, astrological process throughout the entire universe, on large and small scales, everything that happens is work being done and energy changing forms. So there are so many, like even on a molecular scale in atoms, right? The protons and electrons are putting forces on each other, and there's displacement if the electrons are moving around, and so there's displacement of things, and there's energy changing from one form into another, like nuclear energy and electromagnetic energy and all these things. So when all of that happens, all this energy that's changing forms through work everywhere around us, none of that is created or destroyed, which means every single time that you push something or something falls out of the sky or the grass grows on the ground, um, every single process that happens, the energy is conserved. So whatever type of energy there was, maybe the thermal energy or the heat from the sun goes into the plant through photosynthesis and it turns it into stored chemical energy within the plant and its molecules and its bonds. Um, but in all of that, whatever amount of energy entered a process is the same as the amount of energy that leaves it or that results from that process. So that's conservation of energy is the amount of available energy in the entire universe is exactly the same amount of energy that has always existed. We cannot just make more out of nowhere. We cannot just lose or destroy energy and then it's gone. That doesn't happen, right? All of these changes mean if you had 4 joules of spring potential, it turned into 4 joules of kinetic energy. None of it was destroyed. You didn't get more kinetic energy out of nowhere. It just changed from one form into another. Okay, so let's write the equation for this. Because we're going to be using this a lot in a lot of our problems. We'll do some more details on it. I just wanted to introduce it on the off chance we like see a problem and we want to start looking at how conservation of energy affects this. Because there's a lot more to say on systems and things like that. We know a little bit of internal, external forces and things with systems, but we're going to take the initial amount of potential energy. So U initial. And we'll explain and expand on this where this could be gravitational potential, it could be spring potential, we don't really know. Each problem will be unique. In a certain problem, you might have gravitational potential energy at the beginning of whatever's happening, or spring potential energy at the beginning, or maybe both. You could actually have both. So the initial amount of potential energy plus the initial amount of kinetic energy, I'm going to leave a space intentionally, is equal to the final amount of potential energy plus the final amount of kinetic. So that's conservation that just says within a system, and we're going to look at systems again. We'll look at objects and things going on within a system and internal forces or external forces, many of which will be doing work within a system. And we'll say that the total amount of energy that a system starts with here, depending on something we'll call open and closed systems that we'll get into detail later. The total amount of energy at the beginning is the total amount of energy at the end. And if any energy is different at the beginning or end, that would be because there was some work that happened from external forces outside of the system. Sort of similar to when we did external and internal forces with Atwood's machines or systems of objects in Unit 2. Okay, so conservation of energy says throughout the entire universe, the same amount of energy exists all throughout the universe that has always existed. It is simply changing forms. No energy is created out of nowhere or destroyed and gone. And the equation for that is that whatever amount of energy you start with, plus any amount of work done by external forces, equals the amount of final energy that you end up with. So we may see this in problems where we're going to need some more context. We're going to need some more description on open and closed systems before we really get into using this to deal with work and external work and how it affects the energy within a system. But this is kind of the starting point to say we're going to be looking a lot at how much energy did a system start with, how much energy did a system end with, and how does work play into that? Because work causes changes in energy. And even besides the external work from forces outside of a system, there could be internal work from work inside the system, forces inside the system. And that could cause like potential turning to kinetic or kinetic turning to potential within the system. So we're going to see a lot of this. And this is kind of the final piece of tying everything together. There's a lot of concepts in energy that all come together. So energy exists. It's the ability to do work. There's potential stored energy. There's kinetic energy of motion. There's thermal energy for moving particles on a small scale motion. And then work is when a force acts parallel to a displacement that causes changes in energy. So every time work is done, whether positive work or negative work, depending on the angle between the force and the displacement, um, whenever work is done, there's a change in energy, which is appropriately positive or negative. So if you get positive work, there's a positive change in kinetic energy. If there's negative work, there's a negative change in kinetic energy. And throughout all of that, throughout all the energy types that exist, with all the work that's happening and all the energy that's changing from potential to kinetic or kinetic to potential or kinetic to thermal, um, it's always conserved in all of that. So there's not energy being made out of nowhere. There's not energy being destroyed. It is simply changing those forms from one to another through work because of work happening either within a system or from outside of a system. And we'll look more at internal, external forces and work with systems later on. So we'll leave that for now. But yeah, that's we're about to the point where with a little more explanation on conservation and then getting into conservative and non-conservative forces a little bit as well. That'll put us at a spot where there's a lot of things that all come together to begin solving energy problems. But the reason it's my favorite unit is that it's all very tied together and you can make those connections between, oh, there's work happening here. Well, that means that there's a change in energy. Okay, so I could look at changing kinetic energy. Oh, and it's conservation as well. So I can keep in mind that if I can apply the law of conservation of energy here, that energy is not created or destroyed, I can use that equation. And then I have my energy types. I could look at how much potential energy is there. Oh, I know the equation for gravitational potential. It's mg delta y. Or I can find kinetic energy using 1/2 mv squared. The work equation is going to be useful with force and displacement and cosine theta. So all these things are very connected together. It means there's lots of ways to solve problems, and one particular problem might focus more on work, using the work equation based on what you've been provided or the known variables. One of them might be looking at the individual equations for potential energy, spring potential, gravitational potential, kinetic energy. Conservation of energy might be something we use. Work energy theorem, where the work is set equal to the change in kinetic. So there's just a lot to have in your toolbox here, but it gives you a lot of options and ways to approach problems and look at, okay, should I use work energy theorem as an important piece here? Should I use the work equation or individual energy equations or conservation of energy? I need to keep in mind positive or negative work. So there's a lot of moving pieces, but they all come together into this big picture of energy allows for work to happen in these various positive and negative work situations, which causes all these changes in energy going kinetic to potential, potential to kinetic, kinetic to thermal, etc. And conservation of energy sort of governs all of that and is this overarching, like all the things that happen within all that, energy is not created or destroyed, just changing its forms or changing its types. Okay. So cool. That is that is work energy theorem, and a little bit on conservation of energy. Oh, we're going to wait till the next video to explain more on conservation, and this does set us up to solve a good amount of problems. I think with one more video, we'll really be at the point where, honestly, the vast majority, energy is weird because you get to a critical point, and after about videos in here, we'll have just about everything we need to solve the vast majority of problems. But we've already got a good start here. So we will see you all in class. And yeah, thanks for watching. Don't forget to use the Padlet if you want to do any questions or things like that. It's in Schoology below the daily agenda. So check that out as well. Thanks.